Hey everyone, so a couple days ago we talked about cevians, which were just special segments in a triangle. So remember, generally speaking, a cevian is a segment that connects a vertex of a triangle to some point on the opposite side or connects to the opposite side. So the special cevians that we talked about we had angle bisectors, which is pretty self-explanatory, I think. We had medians, so remember a median connects a vertex to the midpoint of the opposite side. And we also had altitudes, and an altitude connects the vertex to the opposite sides at a right angle. And it turns out that if you draw, for example, all three angle bisectors in a triangle, that something really kind of cool happens. And the same thing's true for the other cevians as well. And then there's also a fourth one we're going to throw in there that's not a cevian, but there is something really cool about the intersection of all of if you draw in the perpendicular bisectors of all three sides. So let's take a look at these constructions. So in no particular order, the first one we'll do is, let's do the angle bisectors first. So I'm going to do the angle bisectors of all of the sides. I'm going to walk you through one of these, and then I'm going to finish up the construction and come back. So it'll be kind of like a cooking show, where I have all the ingredients there, I get it all in, and I throw it in the oven, and then magically, voila, it's done, even though it had to bake for a couple hours. Maybe not a couple hours, but you get the idea. So let's take a look at just constructing an angle bisector for one of the angles in the triangle. So I'm just going to pick this vertex here. So to do the angle bisector, remember we put the pointy end of our compass, which is really the center of our circle, on the vertex of the triangle, and then I'm going to draw this arc through here. I'm using colored pencils so that you can see which construction marks go with which angle bisector. And really here, all we care about are these 2 points of intersection here. So you could just draw a little arc here and a little arc here if you want to. Just make sure the arcs are big enough that I can see them. And then you open up your compass to any opening whatsoever. I tend to open these pretty wide so that my construction marks are out here and not really in the way. So I'm going to open up my compass, and from each point of intersection, I'm going to draw an arc out here. And then from this point of intersection, I'm going to leave the compass opening the same, and I'm going to draw an arc here. So if I connect these now, I left my straight edge at school, so I had to make myself a straight edge. So I just made myself a straight edge by folding up some paper. So I'm going to go ahead and connect this to that point of intersection up there, here, and here. So that's an angle bisector. So I missed this point down here, but I'll fix it. So that's an angle bisector. I'm going to go ahead and do that construction for the other vertices as well. So here are my three angle bisectors. And what you'll notice, and if you do this, if you're careful enough, all three angle bisectors intersect at that one point. And that point right there is known as a point of concurrency. So two things are concurrent in this context where they cross. So if you draw all or construct all three angle bisectors and you're careful enough with it, they will all intersect at the same point. And there's actually a name for that point. There's something really special about that point, which is really kind of cool. So let's take a look at what that is. So this point is what's known as the in-center. So it is the in-center. So here's what's special about this point. For any angle bisector, every point on an angle bisector is the same distance from each side of the angle. So for example, let me just put a little sketch over here. If I have this angle and I've constructed the angle bisector right here, if this right here is an angle bisector, if these are congruent, then if I take any point on the angle bisector, it's going to be the same distance from this side of the angle as it is from this side of the angle. And we always measure distance from a point to a line at a right angle. So for example, if you wanted to walk from here out to this road out here, you wouldn't go this way. That's not the straightest distance or the shortest distance. So the shortest distance is always that straight line. Even though this is a straight line, it's not the shortest distance. The shortest distance is going to be if you walk directly towards that road, so that this is a right angle. And same thing here, though that's a right angle. So if I wanted the distance from this point to this side, I would have to figure out what that right angle is, and then this distance and this distance would be the same. And the same is true for any point down here. This distance and this distance will be the same as each other. Now these aren't going to be the same as each other. I hope that's kind of obvious. But every point on the angle bisector is the same distance from each of the sides of the angle. And the reason that matters is that what that means then is that this point right here is the center of a circle that can be inscribed inside the triangle. So an inscribed circle means that the circle just touches in one point each of the sides of the triangle. So we kind of have to, I'm just going to ballpark this for right now, what a right angle would be. I mean, I could construct this, but I just want to ballpark it right now. So if I'm close, if I'm remotely close, what should happen here is if I find that point right there, roughly, where it roughly meets at a right angle. So again, I'm just eyeballing this. We will talk later about how to actually construct this. But for right now, I'm just going to eyeball it. And then when I draw this circle, again, I missed it a little bit. I didn't quite get it just right. But I can draw that circle. This circle right here is inscribed inside the triangle. So meaning, so we're going to kind of use our imaginations a little bit, that the circle just touches in all three of those points. And I know that that has to happen because I know that for this point, it's the same distance from here as it is from here. And I know that it's the same distance from here as it is from here. So all three of those distances have to be the same, which means that all three of those points have to be on a circle where this point is the center. So I'm not going to go through proving that. I think this is going to be one where it's just more of an explanation as to why that happens. So if you can understand why that happens, it'll help you remember that the incenter, that you find the incenter by making the angle bisectors. Because if you want the incenter, you're looking for the point that is the same distance from all three sides of the triangle. And since every point on your angle bisector is the same distance from all the sides, then the angle bisectors is the one that is going to be the one that gets you that incenter. Now, keep in mind that if you were asked to find the incenter, you really only need to do two angle bisectors. Because if you have two angle bisectors, where they cross is going to be that incenter. So you don't actually have to draw all three. You just need any two angle bisectors. And once you've found where they intersect, then drawing in the other angle bisector. The only reason to do that would be if you want to just check and make sure. If you draw in that third one and it doesn't intersect anywhere near here, then something probably went wrong somewhere along the way. But you really can kind of tell when you construct an angle bisector, if the angles are clearly not congruent, you can tell also that way that something just went completely wrong. So if you're asked to construct the incenter, that means you're going to construct at least two angle bisectors of any two angles of your triangle. And where those cross will be that incenter. All right, so next up, again, in no particular order, let's take a look at what happens if we construct the medians for all three sides of your triangle. So let's construct one median together, and then again, I'll go off, do the other two, and come back. So if I'm going to construct a median, let's say I want to construct a median from this vertex up here. What I need is, I need the midpoint of this opposite side. So what I want to do here is, I'm going to kind of do that perpendicular bisector construction, except I'm only going to take that point where it crosses. So remember, to find the perpendicular bisector, I'm going to open up my compass, more than half the length of the segment, and I'm going to put an arc here and up here. Again, I tend to open up my compass a little bit wider for these so that the construction marks are outside the triangle. And then I'm going to leave the same opening, and I'm going to do the same thing from the other side. Here and here. Didn't quite get the one long enough. So there and there. So now again, the reason I did this is so that I could locate the midpoint. So I'm not actually going to draw in the whole perpendicular bisector because that's just going to get in the way. So here, I want that point right there. So that's my median. Or sorry, that's my midpoint. So the median then will be if I connect that to this vertex to the opposite side. So this right here is a median. I'm going to go ahead and construct the other two medians, and then we'll come back, we'll see what happens. All right, so there are all of my medians drawn in. And again, if you did it carefully enough, you'll see that they all intersect here in the same place. So this point right here, this is known as the centroid. So that point that happens, that point of concurrency there, that happens when you draw in all the medians, that's the centroid. So cool thing about this one is if you had, some sort of thicker paper and you did this and you cut the triangle out, this is the balance point. It's the center of gravity of this triangle. So if I were to cut this out, I should be able to balance that triangle right on my pencil. I don't know if I could do it with this paper, the thinner paper, but if you had some kind of like cardstock or something. The other thing that happens here, which is actually more useful, at least for our purposes, is that each of these medians get divided up into what I like to think of as like a longer segment and a shorter segment. And they actually get divided up in such a way that each of the longer segments is twice as long as the shorter segment. So for example, if this were x, this would be 2x. And over here, if this were y, this would be 2y. And if this were w, this would be 2w. So that's a fact you're going to need to know about the medians. So that's going to show up in maybe some algebra kind of problems in this course where you have to write some equations and solve for some side lengths and things like that, or some segment lengths. So make note of that to yourself, right? That the medians, where they intersect, that point of concurrency of the medians is called the centroid, and the fact that it's the center of gravity is just more of a fun fact than anything else. But for our purposes, the useful fact here is going to be that the longer segment for each of the medians is going to be twice as long as the shorter segment of those medians. Right, so the next one we're going to look at is actually not formed by drawing in or constructing any cevians. What we're going to do here is we're going to construct the perpendicular bisectors of each side. So it's kind of like what you did when we found the median. So it's the same process, except instead of drawing in the median, we're going to actually draw in the perpendicular bisector of each side. So again, I'm going to open my compass more than halfway. I'm going to put an arc up here and here. And then I'm going to use that same opening to do the same thing from the other side. And this time now, I'm actually going to go ahead and draw in that perpendicular bisector. And then we're going to do the same thing for the other two sides. So I'll be right back. So this is what that one looks like. So again, you'll notice, and hopefully at this point it's not really surprising to you, that again, if you're careful, those are going to all intersect in the same place. And the name of this point, this is what's known as the circumcenter. So here's what's important here. What we have are the perpendicular bisectors. And if you'll recall from a previous lesson, I mentioned that if you take the perpendicular bisector of any segment, if I take any point on that perpendicular bisector right here, so let's say that this is a right angle and this has been bisected. If I take any point on that perpendicular bisector, it's the same distance from here as it is from here. So this would be an isosceles triangle. Same thing here. If I take this point, that distance and that distance are going to be the same. So because this is a point on all of the perpendicular bisectors, what that means is that this point is the same distance from here as it is from here. It's also the same distance from here as it is from here. So all three of these are the same, which means then that this point, and this point are all on a circle with that point as the center. So circum here, if you think of like circumference, or to circumnavigate means to go around the outside. So the circumference is the distance around the outside of a circle. It's basically the perimeter of a circle. So this is why this is called the circumcenter, because this is the center of a circle that passes through all three vertices of your triangle. So here, again, if I was careful enough, it's probably not going to be exact. So there's some error in our measurement here. My compass really isn't all that precise. So if I put the center of my circle here and open it up so that this goes through one of the vertices of the triangle, this should come at least very close to going through all three vertices of the triangle. So that right there is the circumcircle. So in this case, this circle is circumscribed around that triangle. So the triangle is inscribed in the circle, or the the circle is circumscribing that triangle, and hence the name circumcenter. So for this one, in order to remember that the circumcenter is the perpendicular bisectors, just remember that every point on the perpendicular bisector is the same distance from each end point. So when you've constructed this in a way so that it's the same distance from each of the vertices of your triangle, making it the center of the circle that passes through all of those vertices. So the last one we're going to do, I'm actually going to do two of these. I'm going to change the shape of the triangle a little bit so we can kind of see what happens if we don't have a triangle that's an acute triangle. So the last one left that we have to do is the altitudes from each vertex. So to construct an altitude, what I need is a perpendicular. So if I want to construct the altitude from here, I need something that's perpendicular to this side that passes through this point. So in the video, I showed you one way to do this. If you were in class for the live session, I showed you another way. So I'm going to show you that the alternative way to construct something that's perpendicular to a given line or segment that passes through a given point. So I'm going to open up my compass. I'm going to put the center of my circle right on one end of the side, and I'm going to measure out that distance right there. And I'm going to do it hopefully carefully enough so that this is the same. And then I'm going to copy that down here. And then I'm going to do the same thing from the other end. I'm going to open up my compass so that I'm going to copy that length right there, that distance, down here. And that's actually all I need. I already know that this point right here is on the segment that I want to draw, or on the line that I want to draw. So all I need is one other point, and it's going to be this one down here. What I really have is, if you're curious, this triangle, so this and this would be the same length, and then if I have this imaginary one over here, this and this are the same length. So what I've done is I've made the top triangle and the bottom triangle congruent to one another. So I'm not going to go through a whole proof of that, but so that's an alternative to the way I showed you in the video. So the altitude then is going to be this segment right here. So I'm going to go ahead and construct the other altitudes, and then we'll come back and, you can see, hopefully you can predict that these are all going to cross in the same place, and then we'll talk about what's special about that point. So here's the point of concurrency for all of the altitudes for this triangle. This point right here is what's known as the ortho center. So in this course, we don't use the ortho center much for anything. We mostly are going to do things with the intersection of the medians because of that 2-to-1 ratio. We can center some problems around that. There are some really cool things about the ortho center, but a lot of them are going to be beyond the scope of this course and would require a lot more study to really be able to appreciate all of the things that are true about the ortho center. But one thing worth mentioning that is, again, it's just a fun fact. It's not really anything that you need to know, but it's kind of cool. I went ahead and actually constructed this point right here, which is the circumcenter. So I'm going to draw that in here. So again, this isn't anything that you would do with regard to the construction of the orthocenter, but I just want to draw this in so we can talk about the thing that's sort of the fun fact about orthocenters. And that is that if you take this point right here and reflect it across any side, it will actually land on that circumcircle, that circumscribed circle. Which is kind of cool, right? If I just reflect this and flip it over there, it's going to land here. This would land here, and this would land out here. So the reflection of that point always lands over one of the sides of the triangle, always lands on that circle that we constructed by doing the perpendicular bisectors. So that, again, that's just kind of a fun fact and really a really cool thing about the orthocenter. So one last thing I want to talk about. If we wanted to find the orthocenter for this, so in other words, if I wanted to find the point where all of the altitudes intersected with one another, if you have an obtuse triangle, and I want to construct the altitude from this vertex right here, So I know that the altitude, again, has to be at a right angle to the opposite side. So what's a little bit weird here is that the altitude for this side, or from this vertex, the altitude is actually going to lie outside the triangle. So if you were to construct this, what you'd have to do is extend this side out. And so I would recommend that you do it kind of with a dotted line. And you'll see this sometimes in pictures in your textbook, where sides are extended out like that and they use this dotted line. So if I want to construct the altitude from this point, from this vertex, to the opposite side, I'm going to have to extend that side out in order to do so. So not all altitudes are actually drawn inside the triangle. They are if the triangle is acute, but not if the triangle is obtuse. And then if you have a right triangle, right, if I have a right triangle here, the altitude here is its own altitude. So if I have this right triangle right here, this is an altitude right here, and this is also an altitude. So a right triangle inherently already has two altitudes. So for the orthocenter for a right triangle, that's just going to be right here, because it's going to be the intersection of all three altitudes, and there's one altitude, there's another. So this has to be that point of concurrency. So for a right triangle, that orthocenter is actually going to be that vertex where the right angle happens. So up here, I'm going to extend this out, and then I'm going to go ahead and construct all the perpendiculars, all the altitudes for each side of the triangle. So I just want to refresh your memory on how to construct the altitude from this vertex, using that other option for your construction. So in this case, I'm going to go ahead and open the compass up. Any opening whatsoever, as long as it crosses twice on the opposite side. So I'm going to draw that in there. And then from each of these points of intersection, I'm going to draw an arc down here from both of the points of intersection with that opposite side. And again, I already have one point. I know that this point is on my altitude, so I just need one more. And so there's my altitude. So again, you can choose which of those constructions you prefer for constructing perpendicular to a given line through a point not on that line. All right, so here I've actually constructed two altitudes. You'll notice they didn't cross yet, which is fine. So I'm just going to take that one I drew here and just extend it out a little further until they do cross. So what you'll notice here is that orthocenter right there is not actually inside the triangle. So it's important to note here that if you have your orthocenter is not always going to be inside the triangle like the other ones are. Sometimes it's on the triangle, sometimes it's outside the triangle, sometimes it's inside the triangle. So I'll leave it to you to kind of decide. Hopefully I kind of already gave it away, but to decide how you can determine whether the orthocenter is going to be inside the triangle, on the triangle, or outside the triangle.